जहाँ मैंने कर्सर रखा है, this is one molecule, this is another molecule. मतलब but so far we have been taking identical molecules only. ठीक है, ये दो molecule जो है हमने लिया है. In this particular case there may be three possible, there may be other cases also, like the two molecules may be moving parallel to each other, the two molecules may be moving towards opposite directions, 180 degrees पे भी move कर सकते हैं. Here this particular case is when these two molecules are moving at right angles to each other. ठीक है, so when these molecules will move at right angles to each other, the movement will be somewhat in this direction. This is moving this way and this is moving this way. ठीक है, sorry for this tilted lines. Okay, so that's why when these two, in this particular case, when the two molecules are moving perpendicularly to each other, the relative velocity is given by this hypotenuse. This is over 2 u bar. So इसलिए जहाँ पर हमने u bar लिखा था, that has to be replaced by u relative. Otherwise, the formula is as it is. There's no change in the formula, right? So u relative, what is u relative? U relative is this, root 2 u bar. So your z1 becomes this. ठीक है, is this okay up to this? Who is asking? Varsha? Was it Varsha who
No,
was
ma'am,
asking?
Vishaka.
V? What's your name?
Ma'am, Vishaka, ma'am. Ma'am, Vishaka.
Vishaka, sorry. So यहाँ तक, is it okay up to this? How to get Z1? Here we have removed the, we have gotten rid of the assumption that only one single molecule is moving. Here we have taken into account, we have taken care of the thing that the rest of the molecules are also moving. Both the colliding molecules are moving. Okay, यहाँ तक ठीक है?
Yes, ma'am. मैम बस मैम परपेंडिकुलर वाला केस ही कंसीडर करना है मैम इसमें बस.
यहाँ पर जो root 2 u bar जो है, this is only for the case of perpendicularly moving conditions. ठीक है,
Okay,
कोई
ma'am.
और डायरेक्ट, कोई और एंगल हम डिस्कस नहीं कर रहे यहाँ पे. ठीक है, this is only for the case when the two molecules are moving at right angles to each other. ठीक है, fine. So if
Okay,
you're
ma'am.
able to find out the relative velocity, the relative and they are moving at any angles, then u bar उसी relative value की expression से replace करना है बस. ठीक है, okay, तो Z11 का half से divide किया था, I explained to you, and nobody is asking me, so I think everybody is clear about this. So let's move ahead. And I think all of you must be knowing the difference between Z1 and Z11 also. Z1 and Z11 के बीच में क्या difference है? Can anybody tell me? इसके बाद I'll move ahead. What is the difference between Z1 and Z11? Anji, anybody tell me? यहाँ पर I think we spend around 5 to 10 minutes in class.
मैम
Anji,
Z
बोलो.
को तब कंसीडर किया गया जब सिंगल मॉलिक्यूल को मान रहे हैं हम मोशन में, और Z11 तब है जब बाइमॉलिक्यूलर कोलिजन है.
Bimolecular collisions तो दोनों हैं, but how will you differentiate Z1 and Z11?
Z11 में हमने सभी मॉलिक्यूल्स को माना है मोशन में.
Z1 में भी तो माना है, इस वाले एक्सप्रेशन में भी तो Z1 में भी we have assumed, we have taken care कि दोनों molecules move कर रहे. Your answer, I know you must be मतलब having the correct knowledge, correct concept in your mind, but you're not able to express it. And I feel like that. Chandar, right? You're next. Pratham, can you tell me difference between Z1 and Z1? I think it's time to call you by your names sometimes, ताकि
Yes, ma'am.
मुझे पता चले who is alert and who is not. हाँ जी, बोलिए
Z11 क्या है कि
प्रथम.
हमारा यस मैम Z11 क्या है, हमारा नंबर ऑफ कोलिजन आपको बता रहा है कि वो कितने बायोमोलिकुलर जो कोलिजन है हो रहे हैं. और जबकि जो हमारा Z1 है उसमें नंबर ऑफ जो आपका परपेंडिकुलर वन साइड के पार्टिकल्स हैं उनके बता रहे हैं मोशन में जो है.
The answer is not still satisfactory. Anybody from the girls' side? Shrishti, can you tell me?
मैम ये जो है कोलिजन फ्रीक्वेंसी के टाइप में ये तो है, क्योंकि पहले में जो सिंगल मॉलिक्यूल को कंसीडर किया कितने कोलिजन, बाय मॉलिक्यूल में एक सिंगल मॉलिक्यूल मतलब वहां पर 2 मॉलिक्यूल्स है ना, तो आपने तभी तो उसको हाफ से डिवाइड किया था।
I know, but अब if any unknown person, if suppose the external examiner आके आप लोगों को पूछा कि how will you differentiate between Z1 and Z11, तो the answer should be satisfactory, right?
यस मैम।
Clear मतलब difference बताना आना चाहिए आप लोगों को, ठीक है? I know you have this thing in mind, but not able to express completely, I think. Let me tell you. ठीक है, as the your subscript also suggest, यहाँ पर 2 subscripts है Z11 और यहाँ पर only एक ही subscript है Z1. इसका मतलब Z1 का मतलब है कि it can be Z1, it can be Z2, it can be Z any variable Zn, ठीक है? इसका मतलब है कि Z with a variable, this means कि that one single molecule is undergoing collision with other molecules. Z1 का मतलब one molecule, that molecule number 1 is undergoing collision with all the rest of the molecules. So in both the cases, they signify bimolecular collisions. But when we write only one subscript, Z1 or Z2 or Zn, whatever, in general case Zn, it means that that single molecule is undergoing collision with other molecules. ठीक है, but once we write in double terms like Z11, it will take into account all such bimolecular collisions, all such collisions Z1, Z2, Zn, सारे का sum जो है it will be given by Z11. Is it fine? Do you find any difference between the answer I tell you and the answer you have told me? दोनों ही bimolecular
Z11 सम है।
Z1 जो है it is only one single molecule colliding with the rest of the molecules. तो हर एक molecule के लिए there will be a value of Z1. Molecule 1 के लिए भी Z1 expression होगा, Molecule 2 के लिए भी. But Z11 जो है is the sum total of all the Z1 values. But we don't want any repetition, तो इसलिए हमने यहाँ पे 2 से divide किया है in order to avoid repetition. But लेकिन ये sum ही है. Is this fine? Okay?
ओके मैम।
Yes, ma'am.
चलो, so far we have discussed about, यहाँ पर Z11 दो subscripts लिखा है, but still 11 का मतलब है कि we are considering 2 identical molecules, the 2 molecules which are colliding, all identical bimolecular collisions we are considering. But what if the 2 molecules are not identical? ठीक है, सपोज 2 गैसेस का मिक्सचर लिया हमने, तो उसमें 2 तरीके के गैस मॉलिक्यूल्स होंगे, गैस मॉलिक्यूल 1 एंड गैस मॉलिक्यूल 2. इन दैट केस हाउ विल वी राइट द एक्सप्रेशन फॉर टोटल नंबर ऑफ बाइमोलिकुलर कोलिशंस? यहाँ पर Z12 लिखा है, तो ऑब्वियसली इट विल बी द total number of bimolecular collisions when 2 unlike molecules collide with each other. ठीक है, so बाकी सब सेम है. देखो, if you compare this equation with Z11, the only difference is यहाँ पे U bar के जगह U bar is getting replaced by root over 8 kT upon pi mu, and sigma is being replaced by sigma 1 or 2. That's it. And n star square के जगह n1 into n2 लिखा है, where n1 is the number of molecules per unit volume of type 1. Is my voice breaking again? हेलो
मैम अभी आप यही स्लाइड दिखा रहे हैं ना?
ये बट आप
No, ma'am.
एक्सप्लेनेशन स्लाइड का कर रही हैं?
मैम यस मैम।
स्लाइड मैं तो मूव कर रही हूँ. आई थिंक इट मस्ट नॉट बी मूविंग ऑन योर साइड. अब आ गई है वो स्लाइड, दूसरी नेक्स्ट स्लाइड अनलाइक मॉलिक्यूल्स की.
नो
नो
मैम.
मैम।
देयर इज सो मच नेटवर्क प्रॉब्लम फ्रॉम माय साइड ना, दैट्स व्हाई. अभी भी नहीं.
नो
नो
मैम.
No, ma'am.
आई विल प्रेजेंट
अभी भी वही वाली पहले ही।
दोबारा प्रेजेंट करती हूँ फिर.
Yes, ma'am.
Drop. अब आ गई वो स्लाइड अनलाइक मॉलिक्यूल्स वाले इक्वेशन?
यस मैम।
यस मैम।
Yes, ma'am.
यस मैम आ गई।
ठीक है, ओके ओके ठीक है। तो यहाँ पर Z11 की जगह आई एम रिप्लेसिंग Z11 बाई Z12, ठीक है। बाकी सारे ठीक हो, जो जो भी डिफरेंस है वो बताती हूँ। पाई इज कांस्टेंट, सिग्मा की जगह it is sigma 1 2 square, ठीक है। n star square, instead of n star square I'm writing n1 and n2 का product, ठीक है। and instead of u bar I'm replacing it by root over 8 kt upon pi mu। तो ये एक्सप्रेशन लिखो, मैं एक्सप्लेन करती हूँ वन बाय वन। Equation का format is the same, but many of the terms are getting replaced when you consider the two molecules to be different. लिख लिया? तो यहाँ पे Z12 भी वही है। when once we write two subscript, it always mean the total number of bimolecular collisions. So here Z12 means the total number of bimolecular collisions between two unlike molecules which are one and molecule 1 and molecule 2, ठीक है। तो सिग्मा की जगह it is sigma 1 2, where sigma 1 2 is the average। सिग्मा क्या लिया था हमने previous equation में? sigma is the average diameter of the two molecules, ठीक है। तो यहाँ पे it will be the average diameter of the two molecules again, but it will be sigma 1 plus sigma 2 divided by 2, ठीक है। So this will be different from sigma, because if we talk about like molecules, obviously the diameter will also be different. So that's why sigma 1 2 will not be equal to sigma, or will not be equal to sigma 1 or sigma 2. So we have to take the average of the two diameters. n star square, instead of n star square I've replaced it by n with the product of n1 and n2, ठीक है। where n1 is the number of molecules per unit volume of molecule 1 and n2 is the number of molecules per unit volume of molecule 2, ठीक है। Coming to how u bar is being replaced by this, u bar is nothing but your average velocity, right? Average velocity का simple formula है root over 8 kt upon pi m, है ना। For one single molecule it is written as root over 8 kt upon pi m. For one mole it is written as root over 8 rt upon pi m. One mole के केस में m molar mass capital M लिखोगे, single molecule के केस में pi m जो है mass of single molecule, that is small m, ठीक है। तो यहाँ पे it has been written in terms of, बाकी सारे same है 8 kt upon pi mu, where m is being replaced by the symbol mu, and mu is called the reduced mass. And where this term is used is, reduced mass is used in term where we consider very small particles just like electrons, protons, यहाँ पर molecules, gas molecules की बात कर रहे हैं, so therefore we also assume them to be quite small. So instead of taking the direct average of m1 and m2, we prefer to take the reduced mass. To reduce, how reduced mass is different from average mass is, average mass will be given by m average is equal to m1 plus m2 divided by 2. Average mass will be given by this, right? But how reduced mass is different from average mass is, the reciprocal of the reduced mass will be equal to the sum of the reciprocals of the two masses m1 and m2. तो ये difference है दोनों में. Instead of taking simple average like m1 plus m2 divided by 2, reduced mass is given by m1 plus m2 divided by m1 m2, and this reduced mass term is used when we talk about very tiny particles, ठीक है। So this is Z12, the expressions of all these Z1, the first case of Z1 when we assume, when we have the first assumption कि only one single molecule is moving, फिर वहाँ से Z1 का expression हमने कैसे deduce किया when we take care of the two motion of both the molecules. फिर उसके बाद how we to Z11 expression, then how we come to Z12. This 4 derivations important है, and how the various steps in between you should know. ठीक है, so another term is mean free path, which is the last term for molecular collisions. The mean free path is nothing, as the name also tells you, it is the average distance traveled by a molecule between two successive collisions. When a molecule undergoes two successive collisions, एक collision से पहले मतलब एक collision के बाद दूसरे collision से पहले, how much distance, average distance is being traveled by that molecule. This is what we mean by the mean free path. So formula is here, average distance traveled by the molecule per unit time divided by number of collisions made by a single molecule per unit time. ठीक है, so simply it will be average distance की जगह as average distance will be u bar and number of collisions made by a single molecule per unit time. तो यहाँ पे देखो I'm replacing it by z1 root 2 u pi sigma square n star. ठीक है, star जो है ये ऊपर है, सुपरस्क्रिप्ट आना है मुझे, इसको चेंज कर लेना. Superscript लगाया था, I don't know how it change on its own in equation form. तो u bar cancel हो जाता है, then it comes like this. So this is the expression for sigma lambda, which is known as the mean free path. तो एग्जाम के लिए तो हर चीज जो मैं करा रही हूँ क्लास में, all of them are equally important. ठीक है, and I don't think I'm missing any of the things which are being mentioned in the syllabus. मैं I think हर चीज करा रही हूँ क्लास में. I am not leaving anything to you. एक जो रूट मीन स्क्वायर स्पीड डेरिवेशन करने के लिए बताया था मैंने, उसमें कुछ डाउट आ रहे हैं आप लोगों को, आई नो, देखती हूँ उसका मैं. But from now on I'll also leave something for you people also to do. I think छोटे छोटे derivations तो आप लोग कर ही सकते हो बुक से देख के, and we can discuss in the class also, so that we can have a change in the teaching mode also. तो इसके बाद ही देखो syllabus में you have effect of temperature and pressure on mean free path and molecular collisions. जितने भी हमने molecular collision discuss, Z1, Z11, Z12 and what and mean free path का expression जो उसमें what will be the effect of temperature and pressure. जब temperature vary करोगे, pressure vary करोगे, तो what will be the effect, expression से ही निकालना होता है, right? तो बुक में बहुत अच्छे से दिया हुआ है, and the steps are, all the steps are very very simple. तो आप लोग अपने अपने कॉपी में करोगे and you will show it to me. ठीक है, and I don't think you people will find any problem in understanding those steps, क्योंकि बहुत simple steps है. तो यहाँ करा नहीं रही हूँ मैं, so आप लोग कर लेना आज या कल में and you will show me. ठीक है, and those are very easy steps. खाली आपको रिलेशन देखनी है कि टेम्परेचर और प्रेशर के साथ क्या रिलेशन है विद ऑल दोस मॉलिक्यूलर कोलिशंस एंड मीन फ्री पाथ. ठीक है, तो ये चीज आप लोग कर लेना अपने आप खुद. इसको लिख के रखो और स्पेस छोड़ना, बिकॉज बाद में भूल जाओगे आप लोग, पीपल विल फॉरगेट लेटर ऑन. इम्पोर्टेंट है ये, मैं छोड़ रही हूँ इसका मतलब ये नहीं कि इम्पोर्टेंट नहीं है. दिस इज वेरी इंपॉर्टेंट, इट कम्स वेरी फ्रिक्वेंट इन एग्जाम ऑल्सो, बट वेरी इजी. But I have to write lots of things here, all the equations. So please do it on your own. कोई doubt, I don't think there will be any doubt or any problem in the steps. But अगर कोई doubt आती भी है तो I am there for you. ठीक है? So do this on your own. Next, let's come to this law of equipartition of energy. Does this term sound familiar to you? Law of equipartition. हाँ जी. Has anybody heard of it? Law of equipartition of energy?
Yes, ma'am.
Yes, ma'am.
What is this? पढ़ के मत सुनाना, स्लाइड पढ़ के. Just tell me what you know, what you have in mind about this topic.
मैम इस एक्सप्रेशन के बेसिस पे क्वेश्चंस किए हैं बस.
Definition statement नहीं.
नो मैम,
कौन सी क्लास में करी थी? 12th में, 11 में?
11th में फिजिक्स में किया था.
चलो ठीक है. आई थिंक ये गैसेस स्टेट का मतलब मेनी पोर्शंस ऑफ गैसेस स्टेट आर वेरी मच रिलेटेड विद इनमें इसमें जो टॉपिक्स है, फिजिक्स में भी काफी सारे टॉपिक्स है, जैसे काइनेटिक थ्योरी ऑफ गैसेस है, मोमेंटम है, दे आर वेरी मच रिलेटेड टू फिजिक्स यूनिट्स आल्सो. ठीक है, तो हो सकता है फिजिक्स में पढ़ा हो आपने. तो अकॉर्डिंग टू लॉ ऑफ इक्विपार्टीशन ऑफ एनर्जी, so suppose the energy of a molecule, suppose it can be written in various forms, right? Suppose if it is written in such a form which in the form of a sum of various terms, कई सारे terms के sum की form में suppose लिखते हैं किसी molecule के energy को, right? And terms के sum ऐसा होना चाहिए कि it should be consisting of square of some velocity term. I'm not telling it should be sum of exactly the velocity terms. ठीक है, the square term should be something which is proportional to the velocity. ठीक है, and in that case each term जो है, we can assume that each term will contribute half kT to the average kinetic energy of the molecule. ठीक है, I repeat once again, if we write the expression of energy of a molecule in terms of a summation, in terms of a sum of various terms, but if the terms consist of the square of some terms which is proportional to the velocity, or which is exactly the sum square of the velocity, or in other words which is proportional to velocity terms, we can say that each term जो है sum में जो भी हर एक term जो है that will contribute 1/2 kT to the average kinetic energy of the molecule. ठीक है, सो अब इक्वेशन देखोगे और पता चल जाएगा. देखो, काइनेटिक एनर्जी, एवरेज काइनेटिक एनर्जी जो है, इट इज नथिंग बट हाफ एम यू स्क्वायर बार. ठीक है, सो इट कम्स आउट टू बी 3/2 kT, which we already derived in kinetic theory of gases also applications. ठीक है, so u square bar can be written as in terms of three components, x, y, z components के basis पे ux square bar, uy square bar, uz square bar ऐसे भी लिख सकते हो आप लोग. And all these three are suppose equal. ux square component is equal to uy square component is equal to uz square component. So that's why kinetic energy can be written like this. u square bar को मैंने तीनों components में breakup कर लिया, right? So हर एक term जो है, it can be written as half m u bar x square, half m u y square bar, half m u z square bar. तीन टर्म्स में लिख सकते हैं. ठीक है, तो इसका मतलब ये है कि काइनेटिक एनर्जी को नाउ आई कैन राइट इन टर्म्स ऑफ द सम ऑफ 3 स्क्वायर टर्म्स. तो अकॉर्डिंग टू लॉ ऑफ इक्विपार्टीशन ऑफ एनर्जी, हर एक स्क्वायर टर्म जो है will contribute 1/2 kT to the average kinetic energy. Suppose in इस equation को we can divide it into a sum of 3 terms, right? Half m ux bar square, half m uy square bar and half m uz square bar. तो हर एक term जो है will contribute 1/2 kT. ठीक है, is this fine? Okay, the statement of law of equipartition of energy. ये शुरू मतलब स्टार्टिंग इनिशियल वाले
सेम ही रहेगा
स्टेटमेंट
हमेशा?
समझ लो बिकॉज हाँ जी क्या कह रहे हो?
मैम ये 1/2 kT सेम ही रहेगा ना हमेशा?
1/2 kT सेम ही रहेगा ना हमेशा, मतलब आई एम नॉट गेटिंग।
मतलब मैम मतलब ये जो आप बता रहे हैं कि मॉलिक्यूल जो है ये इतना ही कंट्रीब्यूट करेगा एवरेज काइनेटिक एनर्जी में?
एक एक टर्म जो है इसमें 3 टर्म्स में आप डिवाइड कर सकते हो, एक x कंटेनिंग टर्म, एक हाफ m y कंटेनिंग टर्म, एक z कंटेनिंग टर्म इन टर्म्स ऑफ स्क्वायर ऑफ द वेलोसिटी। ठीक है, तो हर एक टर्म जो है ये कंट्रीब्यूट करेगा हाफ kT। हेलो हेलो, कैन यू हियर मी?
यस मैम, यस
तो
मैम।
वही हर एक टर्म जो है 1/2 kT कंट्रीब्यूट करेगा, राइट? तो ये तो यहाँ पर तो
मैम
एग्जैक्ट
स्क्रीन
वेलोसिटी
पूरी
टर्म
नहीं
आ
दिख
रहे,
रही है।
आगे और भी डिस्कस। हाँ जी,
मैम
स्क्रीन इज
स्क्रीन
नॉट
पूरा
विजिबल।
पूरी नहीं दिखाई दे रही। नहीं मैम, नीचे का दिखाई नहीं दे रहा है, शायद आपने जूम कर रखा हो।
मैंने तो कुछ नहीं किया। इज इट फॉर ऑल ऑफ यू?
विजिबल है मैम।
विजिबल है मेरी स्क्रीन में तो। व्हाट अबाउट द रेस्ट ऑफ यू?
विजिबल है मैम।
हाँ मैम
3/2
विजिबल।
kT तक ही लिखा
Yes,
है
ma'am. Visible.
मैंने। हाँ। यहाँ पे किसी को डाउट है बच्चे? इज एनी डाउट विद एनीबॉडी in understanding the concept of law of equipartition of energy? आगे और भी डिस्कस करेंगे तो यू विल अंडरस्टैंड बेटर व्हेन वी डिस्कस ट्रांसलेशनल एनर्जी, रोटेशनल एंड वाइब्रेशनल। ठीक है, तो हाउ आई एम सेइंग कि each term proportional to the square of velocity component. Why I'm saying like this? Why I'm not exactly mentioning velocity component? ठीक है, प्रोपोर्शनल क्यों मेंशन किया है मैंने यहाँ पे? ठीक है, वो आप आगे हम डिस्कस करेंगे तो और समझ आ जाए। ठीक है, shall we move ahead? I think you have understood. देखो, so since we are talking about the motion of a molecule, movement of a molecule, ठीक है, and I told you in the beginning of my classes also that when the gases are in motion, there are the motion of molecule is of 3 types. ठीक है, एक तो translational motion, the second one is rotational, another one is vibrational. ठीक है, so now we're going to break up this motion into these 3 types. ठीक है, and we will see कि how each type of motion, that is translational motion जो है, how much contribution will be there to the total kinetic energy, rotational motion की कितनी contribution होगी, and vibrational motion की कितनी contribution होगी in the average kinetic energy of a molecule. ठीक है, वो ये इस पे भी डिपेंड करेगा कि आपका जो मॉलिक्यूल जो है whether it is linear or non-linear, whether your molecule is a monoatomic gas, whether it is a diatomic gas, whether it is a triatomic gas. So we will discuss all these possible cases, right? ठीक है, so 3 types of motion के अंदर the first one is the translational motion. ठीक है, I told you in the beginning also that translational motion is just a movement of the center of gravity of the body in a particular direction. So when I mention in a particular direction, it may be either in the x-axis, y-axis or z-axis. ठीक है, तो translational motion में whether you कंसिडर, आप मोनोएटॉमिक गैस कंसिडर करते हो, डायटोमिक कंसिडर करते हो, ट्राइएटोमिक, वेदर आप नॉन लीनियर कंसिडर करते हो, नॉन लीनियर कंसिडर करते हो, डजंट मैटर, इट कैन ऑलवेज मूव इन 3 डायरेक्शंस। ठीक है बच्चे, सो ट्रांसलेशनल मोशन के इट विल हैव 3 degrees of freedom irrespective of which kind of molecule you are taking, whether linear, non-linear, whether how many molecules are there, it will always have 3 degrees of freedom along the 3 coordinate axis. ठीक है, so that's why E translational, that is the contribution of translational motion on the average kinetic energy will be half mu square लिखा है यहाँ पे, and u square can now be broken down into 3 components. यहाँ पे ux square, uy square, uz square. ठीक है, so according to law of equipartition of energy, again हर एक term जो है it will contribute half kT. This will contribute half kT, this will contribute half kT, this will. So E translational will, for a single molecule, will contribute 3/2 kT to the average kinetic energy. ठीक है, this is for translational motion only. यहाँ पे आपको लीनियरिटी, नॉन लीनियरिटी, नंबर ऑफ एटम्स नहीं देखनी, ठीक है? It will always contribute 3 degrees of freedom. So according to which it will contribute a total of 3/2 kT to the whole average kinetic energy of the molecule. So now let's talk about rotational motion. Rotational motion जो है यहाँ पर you will find a little bit of difference here, depending on whether it is linear or non-linear. ठीक है? When your rotation जो है, it is defined as the rotation of the molecule along a particular axis. ठीक है? Suppose let us consider a linear molecule first. Suppose a linear molecule में suppose bimolecular molecule अब consider करते हैं. Suppose this is a bimolecular gas consists of two molecules with masses m1 and m2. ठीक है? And let's suppose there are 3 coordination axes, like suppose these are the x, y, and z axes. Sorry for the diagram, but suppose this is your z axis. Let this be the y axis, and let this be the x axis. ठीक है? And here we can say that ये जो है the molecular axis is along the z axis. ठीक है? So now the molecule can rotate along these 3 axes. It can rotate along the z axis also. It can rotate along the y axis also, and it can rotate along the x axis also, right? But here what is different when you take linear and non-linear cases? In case of a linear molecule, each rotation will be associated with their according moment of inertia, right? तो इसके moment of inertia जो है, it will be equal to Iz. इसके according corresponding moment of inertia will be Iy and Ix here. ठीक है? Is this clear? Every rotation along an axis is associated with a particular moment of inertia, Ix, Iy, and Iz. Okay. So now when the molecule is linear rotation, when it rotates along its own molecular axis, the moment of inertia is 0. That is Iz will be equal to 0. यहाँ पे भी लिखा है मैंने. ठीक है? So that's why when your molecule is linear molecule, we will not consider the rotation along contribution of the rotational motion along its molecular axis, because in that case Iz becomes 0. ठीक है? Why it is like this? यहाँ पर भी देखो, for linear molecule moment of inertia along the molecular axis is 0, so only 2 rotational degrees of freedom are there. ठीक है? And rotational energy का expression है, we can write rotational energy in terms of moment of inertia and angular velocity का square, I omega square. You are familiar with this formula, right? E rotation is equal to half I omega square.
Yes,
ठीक है
ma'am.
ना बच्चे? This is nothing new to you, right?
Yes,
So
ma'am.
since we
Yes,
are
ma'am.
ignoring Iz, so ये वाला term तो 0 हो जाएगा, that is rotation along its molecular axis. So we have to consider the rotation along x-axis and y-axis. ठीक है? So half Ix omega x square, half Iy omega y square. If molecular axis is along the z-axis, Iz will be equal to 0. ठीक? So that's why here again, यहाँ पे if you want to apply the law of equipartition of energy here also देखो, it is consisting of a sum of 2 terms, ठीक है? And the sum of 2 terms where the square term is something which is proportional to velocity. Angular velocity जो है, it is not exactly velocity, but it is proportional to velocity. So according to law of equipartition of energy, we can assume that each term will contribute half kT to the total kinetic energy. So that's why E rotation in case of linear will be equal to this contributes half kT. This term will contribute another half kT, which is equal to kT for a linear molecule. तो इसका मतलब क्या है? The contribution total kinetic energy में किसी एक particular molecule में rotational energy से जो contribution है, that will be kT in अगर वो मॉलिक्यूल लीनियर है. अगर वो मॉलिक्यूल नॉन लीनियर है तो यहाँ पर एक हाफ Iz ओमेगा z स्क्वायर टर्म भी आ जाएगा. So that will give you 3 half kT terms. So that's why it will give you 3/2 kT. तो ये डिफरेंस है दोनों में. Difference between translational rotational and difference between linear and non-linear in terms of rotational energy. ठीक है? I hope I'm clear to you. लिखो, and if you have any doubt, we will discuss. When this chapter ends, I'm going to share some university questions. ठीक है? So you'll go through those question papers, तो अपने आप लोगों को समझ आ जाएगी कि दिल्ली यूनिवर्सिटी question paper में what type of questions come and how frequently the questions are being repeated and which are the important questions. 2-3 papers compare करोगे आप लोग तो खुद समझ आ जाएगा हम लोगों की which questions are which parts are common, which are not, or which parts are important and which are not. ठीक है? Is this okay? Rotational motion. So इतनी contribution होगी.
लीनियर
हाँ जी.
मॉलिक्यूल क्या है मतलब?
चलो लीनियर मॉलिक्यूल, सपोज यहाँ पर तो बाई मॉलिक्यूलर गैस ही कंसिडर किया है मैंने, बाई एटॉमिक मॉलिक्यूल. ठीक है? सपोज इफ वी कंसिडर ट्राई एटॉमिक मॉलिक्यूल, इसमें तो एक ही पॉसिबिलिटी, अगर आपकी मॉलिक्यूल जो अगर डायटॉमिक है तो पॉसिबिलिटी एक ही लीनियर ही होगी. देयर इज नो possibility कि the molecule will non-linear. But if we consider tri-molecular gas like this one, it can be linear also, it can be non-linear also. Linear का मतलब एक लाइन में आना, एक ही पर्टिकुलर एक्सिस में आना, all the 2 or 3 molecules. ये linear है. Non-linear का मतलब water molecule जो है, that is non-linear, where you can see
like
an angle
collinear
being
points.
formed. हाँ जी. Linear मतलब all the 3 molecules
मैम
will be lie on us.
शेप पे डिपेंड कर रहा है ना, हाइब्रिडाइजेशन वगैरह पे.
हाँ जी, वो तो इनऑर्गेनिक पे, हाँ, इट विल डिपेंड अपॉन द हाइब्रिडाइज स्टेट, वो सब तो स्ट्रक्चर पे आ जाते हैं. वी आर डिस्कसिंग अबाउट द केस की लीनियर होते तो क्या होते, नॉन लीनियर होगी तो क्या होगी. ठीक है? हाँ, वो तो डिपेंड करेगा. इट डिपेंड्स अपॉन द इंटरनल स्ट्रक्चर, हाइब्रिडाइजेशन स्टेट ऑफ व्हाटएवर मॉलिक्यूल यू आर टेकिंग. ठीक है? उसके आगे हम डिस्कस कर रहे हैं. ठीक है चंदर?
यस मैम.
Is this fine? What is your question exactly? Structure, suppose
मैम
यहाँ
मेरे
पर
को
हम
ये
ये assume करें कि we know about the structure अगर ऐसा है तो क्या होगा, अगर structure अगर linear है तो क्या होगा, अगर non linear है तो क्या होगा. How obviously it will depend upon the hybridization state. ठीक है? तो वो आप inorganic में पढ़ ही रहे होंगे, this molecular structure में VACPR थ्योरी वगैरह बहुत सारे थ्योरीज है स्ट्रक्चर ऑफ अ मॉलिक्यूल डिफाइन, उसको एक्सप्लेन करने के लिए. तो we are not discussing about that in this class. Okay, so linear का मतलब मेरे simple meaning ये है कि एक ही axis में they are falling. Non linear मतलब they are not falling in one single axis. तो यहाँ पे देखो, यहाँ पर भी even though this molecule contains three atoms, all of them are lying in one single line. Suppose z axis पे lie कर रहा है, तो here also the contribution will be kT only from linear. The rotational contribution will be kT only because your molecule is linear. क्योंकि Iz यहाँ पर भी 0 हो जाता है, so half Izw omega z square will also be 0. ठीक है? Enough explanation.
यस मैम.
So now we have discussed about the first and 2 types of motion. Rotational हो गया, translational हो गया, right? The third one is your vibrational motion. ठीक है? Vibrational contribution कितनी होगी ये देखते हैं. So when we talk about vibrational, the first thing is how to write down the energy expression. ठीक है? ट्रांसलेशनल के लिए we have written in terms of half mv square only, क्योंकि ये just single एक ही direction पे move करते हैं ट्रांसलेशनल मोशन में. रोटेशनल में we have the formula of half I omega square in terms of angular velocity. रोटेशनल मोशन को अगर आप रोटेशनल एनर्जी को एक्सप्रेशन में लिखोगे तो now is how to write down the vibrational motion, how to write down the expression for vibrational energy. ठीक है? So here we will assume that your vibration is simple harmonic vibration. ठीक है? तो एक when a molecule undergoes simple harmonic vibration, when a molecule, I will not say, when the atoms of the molecule undergo simple harmonic vibration, energy of vibration motion is given by this, जो यहाँ मैंने दिखाया है. E vibration is written like this. तो vibrational में what is different is it will take into account both the potential energy and the kinetic energy. ठीक है, तो ये जो है this is the first term is your kinetic energy. This is kinetic energy and this is potential energy. तो kinetic energy जो half mu, हाँ जी, तो vibrational energy का expression जो है vibration energy can be written in as a sum of potential energy and kinetic energy of the molecule. ठीक है, so here and here we are assuming the molecule to be undergoing simple harmonic motion, SHM. Simple harmonic motion, you must be knowing what do you mean by simple harmonic motion. Suppose you have a mean position and the molecule is moving to and fro around about its mean position. That is what you call simple harmonic motion, right? So for that particular molecule, it is a sum of kinetic energy and potential energy. Kinetic energy is nothing but half mv square. V के जगह यहाँ पे dr by dt लिखा है, where because यहाँ पे we are assuming the motion to be the molecule to be undergoing harmonic oscillation. ठीक है, so dr by dt is the rate of change of internuclear distance. How the internuclear distance is changing with time. ठीक है, suppose we have a molecule here, again a bimolecular gas. ठीक है, and suppose this is the mean position from which it is undergoing to and fro motion or simple harmonic motion. ठीक है, so dr by dt is nothing but the rate of change of internuclear distance with time. Time के साथ उसका जो internuclear distance जो है वो कैसे change हो रहा है, that is given by this. So this is simply but the velocity term, right? So mu is, suppose if m1 and m2 are the masses of the two atoms, then mu will be given by 1 by mu is equal to 1 upon m1 plus 1 upon m2, जो मैंने किसमें unlike molecule वाले केस में explain किया था, right? So mu is the reduced mass. You're aware about mu, right? Remember अभी 2-3 slides पहले ही discuss किया था हमने इसको.
Yes, ma'am.
ठीक है, so you are clear about kinetic energy. Potential energy is written like this, half into kf x square, and kf is also known as the force constant or the spring constant also. ठीक है, and r naught is the equilibrium position from which the molecule, the two atoms are undergoing to and fro positions, right? And r minus r naught को in some books it is written as x also. So x is nothing but the displacement from the mean position is called r minus r naught also. ठीक है, so potential energy is written in terms of the spring constant or the force constant. So now here also in the expression for vibrational energy also, here we are going to relate everything to our law of equipartition of energy, right? So coming back to the concept or statement of law of equipartition of energy, here also E vibration also contains sum of two terms, और हर एक term जो है is consisting of a square term, and that square term is something which is proportional to the velocity. dr by dt is also nothing but the velocity term, right? So here also, so that's why E vibration again can be written like this, half kt, half kt, half kt from this term, half kt from this term. So every vibrational motion will contribute kt to the total average kinetic energy. ठीक है, so यहाँ पे we haven't talked about the number of degrees of freedom. अभी आते हैं number of degrees of freedom पे. लिख लिया सबने? Have you written all of this?
Yes, ma'am.
So now let's try to solve कि what will be the, now we have known कि what will be the contribution of translational motion, what will be the contribution from the rotational motion depending on the type of molecule, and now we'll have to discuss कि what will be the contribution from the vibrational motion का एक vibrational motion जो है, one vibrational motion will contribute kT, that we have discussed, right? But our thing is how many vibrational motions will be there, that is also of importance, right? So let's see number of degrees of freedom and average energy of molecules. So first we will discuss about this number of degrees of freedom. Degree of freedom, if we talk in layman common man's term, it is nothing but the number of various directions in which a molecule can move. ठीक है, number of various directions in which a molecule can move. So इसमें जरूरी नहीं कि it can only move in only one axis, it can move in x axis only, it can move in z axis only. So it will give you a combination of all the three types of motion: rotational, translational, vibrational. So all will be taken account of, right? So a molecule, a general formula is a molecule having n number of atoms will have thrice n number of degrees of freedom. So a monoatomic gas, a monoatomic molecule, when a monoatomic molecule to a monoatomic gas will have just 1 degree of freedom, 3 degrees of freedom, sorry. So it can only have translational motion along the x-axis, y-axis and z-axis. If we consider a biatomic gas, ठीक है, for example H2 gas, O2 gas, ठीक है, they will always have linear structure and it will have 3 into 2, that is 6 degrees of freedom it will have. Similarly, for a triatomic gas, it will have 3 3s are 9 number of degrees of freedom. ठीक है, so उन total number of degrees of freedom में से हमें we have to see कि how many of them will be translational, how many rotational, और जो बचेगा from the if we remove the rotational and translational, how many number of degrees of freedom for vibration will be there, वो हम calculate कर सकते हैं, right? तो उसमें से we can always see कि what will be the contribution to the total kinetic energy. ठीक है बच्चे, the first thing is कितने number of degrees of freedom होंगे total is we will subtract, we will see ki how many translational degrees of freedom will be there, there will be always 3. How many rotational degrees of freedom will be there, linear hai to 2 will be subtracted and non-linear hai to there will be 3 rotational degrees of freedom. So number of degrees of freedom for vibration will be equal to total number of degrees of freedom minus जितने ट्रांसलेशनल है जितने रोटेशनल है वो माइनस करके मिलेगा, राइट? तो वही लिखा है यहाँ पे देखो, रोटेशनल 3n number of degrees of freedom है for any general molecule having n atoms. Rotational degrees of freedom is equal to 2 for a linear molecule, 3 sorry यहाँ पे नॉन लीनियर आएगा बच्चा, इसको चेंज कर लेना, 3 for नॉन लीनियर मॉलिक्यूल कर दो, ठीक है? So E translational का जो contribution है will be always 3/2 kT, ठीक है, that is fixed. E rotational contribution जो है linear है तो kT contribution will be there, non-linear है तो there will be 3/2 contribution, 3/2 kT contribution. So our task is to find out how much will be the contribution from the vibrational energy. ठीक है, is it clear to you all? तो
Yes,
तीनों
ma'am.
के contributions को sum करके we can find out the average energy of the molecule. ठीक है, so vibrational degrees of freedom will now be equal to thrice n minus 5 for linear molecule, thrice n minus 6 for non-linear molecule, ठीक है, and every single vibrational degree of freedom will contribute kT to the average kinetic energy, total average kinetic energy. So that is each vibrational motion of freedom contributes kT to the total energy. So now E vibrational linear molecule के लिए will be thrice n minus 5 kT. E vibrational non-linear molecule के लिए 3n minus 6 kT. ठीक है? So now we can find out the E linear means total kinetic energy for a linear molecule, total kinetic energy for a non-linear molecule. Linear molecule के लिए 3/2 kT from translational, only kT from rotational and 3n minus 5 kT from vibrational. Non-linear के लिए 3/2 kT from translational, 3/2 kT from rotational and 3n minus 6 kT from vibrational. So try to understand this too. ठीक है, बाकी आपको कोई सा भी मॉलिक्यूल आपको सपोज देते हैं जिसका आपको नंबर ऑफ एटम्स पता है, तो ओनली बाय रिप्लेसिंग n बाय द नंबर ऑफ एटम्स यू कैन ऑलवेज फाइंड आउट द total energy of that molecule. Monoatomic
Ma'am,
or
can you give one
diatomic,
example?
एग्जाम्पल अभी नेक्स्ट स्लाइड पे देखते हैं. एग्जाम्पल्स पे सीधा ले लो ना. जस्ट ट्राई टू फाइंड ऑक्सीजन मॉलिक्यूल. सपोज O2 मॉलिक्यूल लीनियर है एंड n इज इक्वल टू 2, राइट? सो लीनियर का ये फर्स्ट फॉर्मूला लगाओगे. ट्रांसलेशनल विल बी 3/2 kT. रोटेशनल विल बी लीनियर है तो kT कंट्रीब्यूशन विल बी देयर एंड 3n minus 6 will become 6 minus 5, that is kT. So vibration say kT. So sum total will give you the total energy of oxygen molecule, one single O2 molecule. ठीक है, तो इसको आप 1 मोल की टर्म में भी कन्वर्ट कर सकते हो. K को R से रिप्लेस कर दोगे तो you will find in terms of 1 mole. ठीक है, is there any doubt? लिख लिया ये सारा? Shall I change the slide?
नो मैम, 1 मिनट बस.
नो मैम, वेट
लिखो.
प्लीज.
नहीं नहीं, लिखो. I'll give you time.
एक्सक्यूज मी मैम,
बोलिए.
हीलियम के लिए कैसे निकालेंगे?
He, only He ना. Helium is monoatomic, right?
यस मैम.
Hello. Helium
यस मैम.
is monoatomic. तो monoatomic formula लगाओ. इसमें translational में से 3/2 kT will always be there from translational motion. ठीक है. And how many monoatomic है तो vibration 3 into 1, 1, 3, right? So only translational motion will be there. ठीक है, तो ये नेक्स्ट स्लाइड में देखो. मोनोएटॉमिक गैस E is equal to N is equal to 1 3/2 kT for one single atom, right? Or one single molecule. ठीक है, and for 1 mole it will be 3/2 RT. That's it. There will be no rotational, no vibrational. Vibration तभी possible है when we consider two atoms or there is a change in the internuclear distance. ठीक है, हीलियम के when monoatomic gas में कोई internuclear distance है ही नहीं because there is only one single gas. So the gas can move just only along the 3 axes x, y, and z, which is nothing but your translational motion. Is it fine? Satisfied or not? So
No, ma'am,
monoatomic
not
के लिए मैंने
understood.
evaluate किए. हीलियम जो उन्होंने पूछा है ना, that is a monoatomic gas. मोनो एक ही सिंगल मॉलिक्यूल है उसमें. ठीक है, सो डिग्री ऑफ फ्रीडम कितने है उसमें? थ्राइस n. दैट इज थ्राइस n is 3 into 1 is 3. Only 3 degrees of freedom is there. So those 3 degrees of freedom is reserved for translational motion. translational motion will contribute 3/2 kT. So energy will be 3/2 kT, and that is coming only from the translational motion. It can move translationally along the 3 axes x, y and z. Vibration हम तभी consider कर पाते हैं when we have more than one atoms, because we have to see the change in internuclear distance in case of translation, in case of vibrational motion. तो वो भी possible नहीं है. ठीक है. एंड रोटेशन के लिए भी एक पर्टिकुलर एक्सिस पे रोटेट करना जरूरी है. सो दैट इज आल्सो नॉट पॉसिबल. सो 3/2 kT is the total energy for a monoatomic gas or only a molecule which has just one single atom only. ठीक है. So 3/2 kT is equal to energy for all monoatomic gases. For 1 mole it will be 3/2 RT. So बाकी diatomic और इसमें ट्राइएटॉमिक आना चाहिए, इसमें भी मिस्टेक है. मोनोएटॉमिक गैस के लिए ये है. डाइएटॉमिक ट्राइएटॉमिक के लिए आप लोग कैलकुलेट कर लेना. डाई में तो लीनियर वाला फॉर्मूला ही लगेगा. इन केस ऑफ ट्राइएटॉमिक, द थर्ड केस, इसको आप चेंज कर दो. इट शुड बी ट्राई. ठीक है. ट्राई में यू हैव